So now we start our discussion with the next topic. It is the rotation about fixed axis, right? Rotation about fixed axis, fixed axis. Rotation about fixed axis, the examples, the motion of the fan, right? If you consider the fan, right? This is the fan, suppose, right? This is the fan and this is the axis of rotation. So about this is the fixed axis, right? Or the rotation of the door of your room, right? This is about the fixed axis. But before this, we will revise something. Suppose if a particle is moving like this, right, and its velocity is v and the position vector is r, and it is rotating in a circular path, right, this, and the angular speed is omega. Although v is equal to r omega is the relation between the linear velocity and the angular velocity, in vector form v is equal to omega cross r, right? This is the relation. If the speed is increasing, continuously, if speed is increasing, for example, if you switch on the fan, so just switch before the switch on the fan, before the switching on the fan, its speed is 0, but after some time slowly the speed is increasing. So if speed is increasing, omega is increasing. If omega is increasing, there will be the alpha. What is this? Say angular acceleration. So what is the angular acceleration? Say d omega upon dt. Are you getting? If speed is increasing, there will be some tangential acceleration, dv upon dt. And I think you know this, if this is the v is equal to r omega, so et is equal to r alpha, if you remember. So it is the vector form, then the tangential acceleration is equal to alpha cross r, right? So this is the formula, relation between the velocity and angular velocity. This is the relation between tangential acceleration, and this is the angular acceleration, right? Copy this. So now we will try to understand the rotation about fixed axis with few examples. For example, if we have, this is the rod, right, and it is hinged over here, all right, like this, and it is connected to the string like this. This is the rod of mass. What is the mass? Is equal to 10 kg, and the length is equal to 4 meter. Is it clear or not? This is the 4 meter. Is it clear? And it is hinged over here. So this is string AB, right? Find the angular acceleration. If we just after cutting the string AB, right? This is the first part. Also find the hinge force, right? Hinge force mean the force applied by this support. Also find the hinge force at this point, right? Copy this. So I think this is not discussed in your coaching. Tell me. Right, listen one thing. Before doing this question, right, the rotation motion is very much similar to the translation motion, right? If this is the mass m and the force F is applied, what will be the relation between F is equal to ma? F is equal to ma. F is the force. Because of force, this is the inertia and this is the acceleration. In the same way, if a body is rotating about the fixed axis, suppose like this, and you apply the force, so because of this force, the torque will be applied. So the role of the force in the rotation motion is played by the torque. The acceleration is alpha, and instead of the inertia, it is the moment of inertia. So torque is equal to I alpha. Whenever you want to find the angular acceleration, in this case the acceleration is force divided by mass m. So you have to find the net torque, and you will divide the moment of inertia, then the angular acceleration will be found, right? So listen one thing. After cutting the body, after cutting this string, when you cut this string, so what will happen? Initially it is in equilibrium. It is the condition of rotational equilibrium. In the rotational equilibrium, we have found the tension in this string, but we are not going to find the tension, right? When the string is cut like this, so what will happen? You tell. This is the hinge, right? So what will happen? You tell. If it is the hinge, so initially it is supported by this string, rotation equilibrium. When it is cut, it will start rotating like this. Are you getting or not? So you have to find the angular acceleration just after cutting the string. They have cut the string right now, and at that point you have to find the angular acceleration. To find this, the net torque you have to find. This is the rotation about the fixed axis. This is the axis of rotation. Are you getting or not? This is the axis of rotation about which this rotate will rotate. You tell me, when this string is cut, the tension become 0. So how many force will act upon this rod? Say one is gravity force and this is the hinge, right? So when there is a hinge, I don't know exactly direction of the hinge force. So I will assume this is the N1 and this is the N2, horizontal and the vertical component. So how many forces are acting, you tell? 1, 2, 3, we can assume, right? So can you find, if this is the axis of rotation, the torque about O, right? Because torque is required to find. What is the torque about O? Yes. What is the torque about O? The torque of N1 is 0. Torque of N2 is 0. Only which force will provide the torque? The mg will provide only the torque. In which direction? This is the direction of torque. What is the torque? Say force multiplied by this distance is L by 2. Is it clear or not? Mg into L by 2. Are you getting? And the net torque is equal to what? Put it equal to I into alpha. I into alpha. So what is the moment of inertia about this one end? Can you tell me what is the moment of inertia of the rod about one end? ml square by 3. So I will put the value of the moment of inertia. ml square by 3 into alpha is equal to mg into L by 2. Right. So here what is the alpha? Alpha is 3 upon 2 G by L. Is it clear or not? LL will cancel out. So what is 3 by 2? 10 L is 4 meter. So this is 5. 15 upon 4. Alpha is equal to 15 upon 4 radian per second square. Just after cutting the T. Just after cutting the string. Is it clear or not, you tell? So this is the first part I have solved. The angular acceleration, to find the angular acceleration about this axis, you have to find the torque, and torque put it equal to I alpha, you will get the angular acceleration. Is it clear or not? Copy this. Now listen one thing. We have to find the N1 and N2, right? It is a initially it is a little very interesting and it seemed to be very tough, right? Because to find a small force, we have to do the very good exercise. For example, listen one thing. If this is the body, right? This is the body. It start rotating with some angular acceleration alpha. What is the direction of the angular acceleration alpha? Listen one thing. As F is equal to m into A, in which direction the net force is over there? The acceleration is in the same direction. The torque is equal to I alpha. This is the vector form. So in which the net torque is acting, what is the direction of the alpha? The same direction the angular acceleration will be. Are you getting or not? So what is the net torque about this axis? Like this. So the angular acceleration alpha will also be in this direction, into the board, not clockwise, not anti-clockwise. Rather, the direction of alpha is into the board. Direction of torque is into the board. Is it clear or not? Right. So now if a body is rotating with angular acceleration alpha, if this is the center of mass, right? So what will be the acceleration of the center of mass? Listen one thing. If I consider this the point P and this is the center of mass, the acceleration of point P, you have to find the acceleration of center of mass, you have to find. So what the relation we are going to use? A is equal to R alpha. So if you want to find the acceleration of AP, so AP is equal to what? Say, because this is the point when you consider this the rod is rotating about this axis of rotation. So all the point will start performing circular motion about this axis. All the points, suppose this is the Q point, this Q point is also performing the rotation motion or the circular motion. So its acceleration will be AQ, suppose, right? So what is the acceleration AP? Say R into alpha. So what is the R here? The distance is L. So L into alpha. Is it clear or not? So alpha is what? So alpha, you can consider this is the alpha. Are you getting in terms of L? So what is the acceleration? This is L into 3 by 2 G by L. So the acceleration of this point P is 1.5 G. Are you getting or not? In the same way, what is the acceleration of the center of mass? The acceleration of center of mass will be R alpha. So what will be the R over here? Say L by 2. L by 2. L by 2 into alpha. So the ACM will be equal to L by 2 into alpha is 3 by 2 G by L. So this is 3G by 4. So this is the acceleration of the center of mass. It means as you are moving away from the axis of rotation, the acceleration of every point P is increasing, right? If you are coming towards the axis of rotation, the acceleration, tangential acceleration of the point is decreasing, right? So although we need the acceleration of the center of mass, but any point acceleration is you can find using the A is equal to R alpha. Although the acceleration of each point will be different, but the angular acceleration for all the points will be same. You understand this? Copy this. Now we have found the acceleration of the center of mass. We need to find only the acceleration of center of mass, whether they can ask the acceleration of any point. Now can you make the FBT of this center of mass once again? Right. This is the center of mass. What is this acceleration at this time? The acceleration of the center of mass is ACM. What is that? 3G by 4. And what is the direction of the acceleration? If this is the center of mass, what is this acceleration? Say in this direction. What is that? The ACM is 3G by 4. Are you getting? And can you tell me, I'm writing here the ACM is equal to downward direction 3G by 4. And can you tell me how many forces are acting upon this? The mg, right? The mg, and I assume it is what? It is N2 and it is N1. Are you getting? If you choose this is the x-axis and the y, if you choose this is the x-axis and assume to be y-axis, you tell me what is the acceleration of center of mass in x direction? Yes, all the acceleration of this rod is downward direction. So what is the acceleration of x direction in center of mass? Say 0. Only the acceleration of the center of mass is in y direction. I have chosen this the y direction, and this is equal to 3G by 4. Are you getting or not? You tell. Right. So in x direction, the net force is equal to mass into acceleration of center of mass in x direction. I have to apply. What is the net force in the x direction? Only the N1. Is it clear? And what is the acceleration in x direction? 0. So if no acceleration of this rod of the center of mass in this direction, so N1 must be 0. So here no normal reaction in horizontal direction is applied. Are you getting or not? But in y direction, you tell me how many forces are acting. The mg downward and N2 upward. And what is the acceleration of the center of mass? Acceleration is vertical downward. So in y direction, the net force is equal to m into acceleration of center of mass in y direction. I will apply. Right. So can you tell me what is the net force in y direction? Yes, Varsha, N2 and mg is acting. Tell me, what is the net force in the y direction? mg minus n2. Why n2 minus mg not? Because acceleration is downward, so this force you have to take more, right, than this. So mg minus n2 will be m into ACM in y direction is 3g by 4. So this is mg minus n2, 3 mg by 4, and n2 will be equal to mg minus 3 mg by 4. So n2 will be equal to how much? Mg by 4. So this is the normal reaction n2. So if n2 and n1 you have find, so we can find the hinge force. What is the hinge force? I am writing here. The hinge force is nothing but root over n1 square plus n2 square. But n1 is 0, therefore it is equal to n2 and it is equal to mg by 4. So this is the hinge force. Do you understand this solution, Varsha? Copy this. So I think this question is clear. So this is the rotation about fixed axis. Again I am explaining what type of the question they will ask. There will be system, the axis is fixed, right? Axis is fixed and it will start rotating. It may be the disc, it may be the sphere, it may be the rod. Generally the most of the questions are the disc and the rod, right? So they will ask the angular acceleration. Once you find the angular acceleration, the ACM is equal to R alpha. You will apply the center of mass acceleration you can find. And when the center of mass acceleration is found, then the remaining part you can solve by yourself, right? That is the thing. So let's see a few more examples, right? So I am giving you one more example. Suppose this is the disc, right? This is the disc, and this disc is fixed about this axis, right? Like this, right? This is the fixed axis, axis of rotation. So, and the mass of the disc is, the mass is suppose the 20 kg and the radius is 1 meter. Suppose, okay, suppose this is the 2 meter radius. Is it clear or not? And a string is wrapped over this. The string is wrapped like this, right? The string is wrapped over this, over the circumference, and here you are sitting, you are standing, right, like this, and you are applying the force and you are pulling this by the applying the force, and the force is supposed to be 100 Newton, right? And this is the axis of rotation. So it will start rotating like this or not, you tell, right? So if F is equal to 100 Newton, so you have to find first the angular acceleration, alpha you have to find, all right? And if it start from rest, right, omega naught, if the initial angular velocity, after some time it will start rotating. If initial angular velocity is 0, start from rest, find angular velocity omega after t is equal to 5 seconds. This is the question. Fine. So the thing is same, right, as we do in case of rotational motion. To find the angular acceleration, you must need to find the torque. This is the axis of rotation. This is the question of the fixed axis of rotation about fixed axis, right? So listen one thing. Although there will be the mass 20g, listen, the mass of this rod is what? Say mg, and the normal reaction applied by this hinge or by support is n. So can you find the first, the torque about axis of rotation? This is the point O, torque about O. Yes, tell me, what is the torque about O? The mg and normal reaction torque is 0, and this is the line of action of force, only this axis. So what is the torque? Can you tell me? Yes, Varsha, this is the force and this is the perpendicular distance. Yes, what is the angular acceleration or the torque direction? Out of the board. Out of the board, you will take the positive sign. Why I am writing positive, negative, then the complex question will come, then you come to know how to, what is the use of this out is taken as the positive sign, right? So this is, the net torque is what? Force multiplied by perpendicular distance, and the radius I can write it is r, and net torque is equal to what? Say I alpha. So the alpha is equal to force multiplied by I. And what is the moment of inertia of the disk? The moment of inertia of the disk I am writing here, half mr square, if you know, right? So alpha is equal to what? Alpha is equal to F into R is equal to half mr square. So this is 2F upon m into R is the angular acceleration. So the value is 2 into 100 into 20. The radius is 2. Are you getting or not? 2 will cancel out. So 5. So angular acceleration is 5 radian per second square. So this is the angular acceleration. This is the angular acceleration. So after some time, when you are pulling this, right? So it start rotating, the angular speed continuously increasing. So how to find the angular speed after 5 seconds? So in the second part, the omega is equal to omega naught plus alpha t I will apply. The initial angular velocity is 0 because according to question it start from rest. What is the angular acceleration? Say 5. The time is 5. The omega become 25 radian per second. I think the question is clear. Copy this. Okay, so instead of this, I am taking another similar example. You can do this by yourself. Suppose there is a disk, right? And the disk is of mass m. The mass is suppose the 10 kg, right? And the string is wrapped over there. Are you getting? And a small mass m is hanging. And the mass m is of, suppose small m is 2 kg. Are you getting or not? So this is the center of mass. This is the axis of rotation about which it rotates. If it is released from rest, what will happen? You tell. This is the disk. Are you getting? Or sometime in some question the disk is given like this, right? So this is the axis of rotation. So when it will rotate like this, so it will fall down or not? You tell. So it will moving with the acceleration. This particle will perform translation motion and this disk will perform the rotation motion. Are you getting or not? So its acceleration is a in the downward direction and its acceleration alpha will be in this direction. And if we assume the tension is T, right, and the radius of this is the 1 meter. Are you getting or not? So you have to find first the acceleration of this block, right? Second, the tension in the string, right? Third, the angular acceleration, tension in the string, and the angular acceleration of disk. Angular acceleration of disk, right? And the acceleration of block and the tension in the string. This thing you have to find. The capital M is 10 kg, small m is 2 kg, and the radius is 1 meter, right? Copy this. So let's see how to solve this question. This is performing translation motion. This is performing rotation motion, right? Okay. So in this case, you tell me. This is the question. The solution you can make here, right? The solution. A beautiful figure you can make like this. If this is the small m, so how many force will act upon this? T and mg, and it is coming down with the acceleration, right? If you consider the disk, right, the disk is what? The capital mg acting here, the some normal reaction or tension T dash you can assume. If it is hanging with this rod, or the T dash will be there, and the tension T will be acting in this way. Are you getting or not? This is the mg. So it will perform translation motion and it will perform angular motion, angular rotation motion. So for this block, what will you write? You tell. F net is equal to ma. What is the net force you will write? Say mg minus T is equal to ma. Is it clear or not? Right. This is the equation number 1. And what is the equation you will write? For this disk, you will write net torque is equal to I alpha. Is it clear, Farshad? Can you find the net torque about O? About O, I am asking. About O. Because this is the axis, fixed axis. So what is the torque of mg and T dash? Say 0. Is it clear? Who is applying the torque? Who is applying the torque? this T is applying the torque. How to find the torque? The torque is equal to force multiplied by perpendicular distance to the line of action of force. So the torque is T into R. Is it clear or not? You tell. And which body is this? This is the disc. You may write. This is the disc. So can you tell me what is the moment of inertia about this axis of the disc? Mr square by 2 into alpha. So what is the tension? Mr alpha by 2. Is it clear or not? Very good. You tell me, if the acceleration of this point is A, the acceleration is A, acceleration of this point A, what is the acceleration of this point? A. And acceleration of this point is A, and this is alpha, this is R. Can you tell me what is the relation between A and R and alpha? Yes, this point having the acceleration A is equal to R alpha. So this is the one more condition we have. The relation between the linear acceleration and the angular acceleration. Right. So A is equal to R alpha. Very good. So here A is equal to R alpha also we can apply. So R alpha may be, this is the capital M. The capital M mean this is the capital M and this is the small m into A by 2. Right. This is the equation number 2. Right. So now you can solve this. Put here, solve equation 1 and 2. So mg minus, put the value of t, capital M A by 2 is equal to m into A. So this is the mg is equal to A, small m plus capital M by 2. So what is the acceleration? Say mg upon m plus capital M by 2. Although I am not putting the value, right, of the small m, you can put here only, right? It will be easier for you. So small m is what? Say 2 into 10 upon 2 plus capital M is 10 by 2 is equal to 20 upon 7. So the linear acceleration of this block is 20 upon 7 meter per second square. Is it clear or not? I am explaining once again. This is performing translation motion. So F net is equal to ma. This is performing rotation motion. So torque is equal to I alpha. And the relation between A and alpha is equal to A is equal to R alpha. You have to understand. Solve them. The acceleration, if you know this acceleration A, this is the first part you can think. Right. In the third part, what is the third part? The angular acceleration. So alpha is equal to what? Say A upon R. What is the angular linear acceleration? 20 upon 7. What is the R? Is 1. So alpha is equal to 20 upon 7 radian per second square also. Right. Is it clear or not? Varshas. In the second part, the tension can be found ma by 2. What is the capital M? It is 10. What is the acceleration? 20 upon 7. It is 2. So it is 100 upon 7 Newton is the tension in the string. Is it clear or not? Copy this. I am taking one more illustration. Suppose this is the rod. Right. The rod of length L, the mass M is over there. Right. The mass you can assume to be the M. Are you getting or not? The M. And the length is L. Although in this question, in your book, the rod is massless. Right. But I am taking the mass. And this is the hinge. Right. Like this. It can rotate. If this is L, the one mass, now there are two masses. Right. I am assuming, suppose this is the 2M and this is the M. Right. So if this is the 2M mass is placed at distance L by 3, right, another mass is placed at distance, suppose it is at 12 by 3, and this is the rod of mass M itself. So when it is released from rest, it is horizontally when you have kept right tight and when released. So what will happen? You tell, what will happen? This is the horizontal axis of rotation and the system is start rotating about this. So as soon as it is released from rest, right, as soon as this system is released from rest, you have to find the angular acceleration. This is the question. Is it clear or not? Copy this. So To find the angular acceleration, we have to apply torque is equal to I alpha. So I am finding first the moment of inertia, right? So the moment of inertia is of the rod about one end of the mass m, say ml square by 3, and this is the 2m mass at distance m into r1 square l by 3 square plus this is the mass m into l by 3 square, right? So this is ml square by 3 plus 2m into l square by 9 plus ml square by 9. So LCM is 9. So this is 3ml square plus 2ml square plus ml square. So how much is it? 3ml square by 9. So 2 by 3 ml square is the moment of inertia. This is the first thing. All right. Now the torque about O, if this is the axis of rotation, so net torque about O, right? What is the net torque? Listen one thing. This is the 2 mg, right? This is the mg and this is again the mg. Are you getting? So this is the 2 mg. Should I make over here? If this is the mg acting mg and this is the length L by 2 about O. Although the N1 and N2 torque will be 0, I am not writing that. The net torque is mg into what is the perpendicular distance? Say L by 2. Right. This is the 2 mg. And what is the perpendicular distance? Say L by 3 plus 2 mg. Force multiplied by perpendicular distance. What is this perpendicular distance? Say L by 3. There is another mg. And what is the perpendicular distance? This is say 2L by 3. Mg into 2L by 3. Are you getting? So this is mgl by 2. Right. It is 1 by 2. It is 2 by 3. It is 2 by 3. So if you take the LCM, 6, 3 plus 4 plus 4, it is 4 4 12 or 3, 4 4 8 or 3, 11 mgl by 6 is the net torque. So the net torque we have found, and we have found the I. So then the torque is equal to what? So torque is equal to I alpha. What is the net torque? 11 mgl by 6. What is the moment of inertia we have found? It is 2 by 3 ml square. So alpha we can find, right? So what is the alpha? The alpha, when you will calculate, 3 duni 6, 11 by 4 and G by L is the correct answer. So this is the angular acceleration. Copy this.